Hi, my name is Mr. Evangelista, and welcome to another episode of Advanced Science. Hope everyone's doing well this week. This is the free response question you guys are supposed to do over the weekend. Let's go over it. Okay, so we've got a tabletop here. We've got block A, and it's on top of a negligible friction tabletop, so no friction here. And it's attached to a massless string to a massless pulley. Pulley's negligible mass, negligible friction, and they're released from rest. And then it's attached to block B. Okay. Suppose the mass of block A is much greater than the mass of block B. Estimate the magnitude of the acceleration of the blocks. So this is as a system. The blocks as a system after release. Okay. Notice that they're connected by a string, so their accelerations will be the same. If block B moves, block A will move as well because they're attached by a string. Okay, so think of it this way. Think block A is really, really, really heavy. Okay, so think this is really heavy because we said much greater. And think this is really light. Okay, so think of this as kind of like a feather or a leaf or something. Okay. If this is really light, this won't pull on it that much. Now there's no friction here, so even if you pull a little bit, it'll still accelerate. But the acceleration will be, you can say, close to zero, or very small, or some other things. If you put 0, I think they accepted that as well, but very, very small. Okay. Now suppose it's switched. Suppose that this block B was really, really heavy, and then block A was a leaf or a feather. Okay. Estimate the magnitude now. Okay. That means that there's very, very, very little force tension here. Right? And a lot, it's really heavy, so we have a lot of force gravity. Okay, this is as if we were in free fall. Very, very close to free fall, right? Free fall, so it's close, very close to 9.8 or 10, whichever one you would use. Okay. Now, the way you explain this is because block A, it has a lot of mass, and so has a lot of inertia. Okay, objects, that's Newton's first law, right? Inertia, objects at rest tend to stay at rest. And so the leaf will have a hard time overcoming the inertia of block A. So it will accelerate it very little. Whereas with block B, I'm sorry, in this scenario, we are very close to free fall because this is opposing the free fall motion very, very little. They want us to draw a free body diagram for the two blocks here. Okay. Notice, guys, this free body diagram was worth 3 points, and the entire question itself was 12 points. So you get 1/4 of the points just from drawing a correct free body diagram. These are very easy points, so make sure you get them right. Okay. Let's look at block A. So block A is on this tabletop, no friction, and is being pulled by this string. Okay. So being pulled by the string, force tension. It has mass, so it's got force of gravity. And it's on the table, so it has force normal. Notice that the y directional forces are balanced, so there's no acceleration in the y direction. However, if there's a acceleration in the x direction because it has this force tension. Okay. What about block B? Block B has mass as well, so it's got a downward force of gravity. Okay. Now, them saying this, no, that's just to tell us not really to care much about the magnitude, right? Because if I draw this force tension longer than the force of gravity, we'd actually be accelerating upward. If I were to draw it shorter than the tension and force of gravity, it would actually be going downward. Okay? So this is how you get your 3 points. They gave you a point for drawing the force normal, for drawing force gravity and for drawing the force tensions. Okay, derive an equation for the acceleration of the blocks. Okay, remember this has a pulley in it, so let me just redraw. So here's A, and here's B. Okay, our forces that we drew are force tension this way, and force of gravity this way. Okay, we also had force of gravity going down and force normal going up. Okay, remember with pulley problems that go in several directions, we have to establish which way is the positive direction. So let's establish this way, right and down, as the positive direction. Okay, then from there we are gonna say the sum of the forces equals ma. Okay, and now let's sum the forces. So all the forces going this direction and down are positive, and all the forces going in the opposite direction are negative. Do we count this force normal and this force gravity? No, we don't, because it's not in the direction of the acceleration. Okay, so we have a positive force tension here. Then we've got a negative force tension here. Then we have a positive force of gravity. And this is block A. This is block B. So the force of gravity is caused by block B. This is the mass of the system because we're looking at both blocks. So mass of A plus mass of B. And this is all times acceleration. Okay. The force tensions cancel out, so we're left with force of gravity B divided by ma plus mb equals our acceleration. Okay. And then we just break down force of gravity D into mass of B times G all over ma plus mb equals A. Okay, so here's our expression. All right. Now, they're saying, does this make sense? Okay, think about this. So where the mass of block A is much less than the mass of block B. Okay, so we're saying this is block A here is a feather and block B is really heavy. That means that the mass of A is pretty much 0, right? So let's say the mass of block B is 10. So that's 10 G over 0 plus 10, right? And that equals our acceleration. That means this is 10 over 10, which is equal to 1g equals A. That means our acceleration is free fall, 9.8, right? 1 times 9.8 is our acceleration. Okay. Now, let's consider the other scenario where we said A was really heavy and B was 0, pretty much 0. Okay. So we said B was really light, so 0g. And then A is really heavy, we'll call 10 really heavy, plus 0 equals A. Okay, this comes out to about 0. Okay, 0 over 10 is 0. That means the acceleration is very close to 0. This is why this expression, yes, it does make sense, based off of our reasoning. Okay, so now we have a scenario where this pulley is not massless. Okay, this pulley is hard to turn now. Earlier, it was massless, so it was easy to turn. Now, it would say that the pulley of negligible mass is replaced with mass is not negligible. Okay, so here's our normal pulley. And then think of this second scenario here. We now have a really big pulley, something with a mass we cannot ignore. Which one is going to have more force tension? Case A or case B? Okay. So that's what they're asking. Correct answer is there's going to be more tension in case 2. Okay. Why is that? Okay. Why does this string have more tension than that one? Okay. Well, if you think about it, it's going to take more. If we look at the free body diagram here, okay. If this is bigger, are the blocks going to accelerate faster or slower? They're definitely going to accelerate slower. So if you think, let's go over here. If you think this is the free body diagram for the first one, right? The force of gravity is longer than the force tension. That's why it would accelerate. How do I get this to go slower? Because making this really heavy would make this system accelerate slower because there's this massive object we now have to move. So how do I make this slower? Okay, right now it's going, this force of gravity is longer than the force tension. Okay, to make it slower, I have to increase the force of tension, right? To make this now almost equal to the force of gravity, that means there's almost no net force, so almost no acceleration, where this one has greater net force, right? So a greater acceleration. So that's why our answer is that the tension in string 2 has to be greater than the tension in string 1.